Okay, welcome. Today we're going to learn about integrating using partial fractions. So we're only going to focus on the type that have linear, non-repeating factors, and I'm going to talk more about that in a minute. But before I get into how to integrate using partial fractions, I want to give you an easy example that you're going to build on. That is the foundation of this. So sometimes I usually write this as an aside. So we're going to just start with this little aside that will get at the big idea of partial fractions. Suppose I have two fractions, 1/3 plus 1/2. I think everyone knows how to add fractions, two fractions. What we would do is we would start by getting a common denominator. And in this case, to find a common denominator, you'd start thinking of multiples of the larger factor. So 3 times 1, does 2 go into 3? No. So then you'd say 3 times 2 is 6. Well, good. 2 goes into 6, so 6 would be called our lowest common denominator. And how would we get an equivalent fraction to 1/3? Well, everyone knows how to do this, but we would multiply the numerator and the denominator by 2, because 2 over 2 is equivalent to 1, and so 2/6 is the same as 1/3, and 1/2 is equivalent to 3/6. So basically you have 1/3 plus 1/2 is equal to 5/6. So the idea behind partial fractions is, given a fraction such as 5/6, from what two fractions do I add to get 5/6? So this was our answer when I add 1/3 and 1/2. And partial fractions gives you the answer, and you have to come up with the parts or the pieces, the fractions that might add together to give us 5/6. In this case, you could say 1/6 and 4/6. Or you could say 2/6 and 3/6, as we say up here, 2/6 and 3/6. But these can be reduced to 1/3 and 1/2. And the idea is to try to figure out these two given this. So this is the direction that we're going to go in. So I think the best way to do this is to give you a concrete example, and there are two ways to integrate using partial fractions. There's a more difficult way, and there's an easier way, or a shortcut way. I'm going to show you both, and then you can choose whichever method you want to use. Okay, so let's start with a concrete example. I'm thinking of this integral. Okay, so how would you know to use partial fractions as opposed to one of the other methods that we've learned? Our first method of attack, we would usually try to think of u substitution. In this case, maybe you would let u be what's in the denominator, and you'd ask yourself, is the numerator the derivative of the denominator? Well, if you let u be x squared minus x minus 6, then you see that du is 2x minus 1. Clearly, the numerator here is not the derivative of the denominator, so it's not going to go into the natural log. So that method won't work. This is why we're going to need to look at this method called partial fractions. And the way this works is we're going to start off with this fraction, just as we would have with maybe 5/6. And you're going to try to think of maybe 2, sometimes it's 3 or 4, but in this case, since it's a quadratic, I know I can factor this into the product of two binomials. Let's take a look at that. X and maybe 3 and 2. We want the middle term to be negative. So the product of these two binomials will give us this trinomial. So one of the factors would be x plus 2, and the other factor would be x minus 3, because those will give you the product of these two linear, these are both linear factors, will give us this denominator. So I'm just going to cross that out for now. And I don't know what goes in the numerator here. That's my goal, is to figure out what are the two fractions that add together to give me this resultant fraction. So this is now an Algebra 1 problem, really. What we're going to try to do is get rid of the fraction, and we could multiply both sides by this common denominator, or x plus 2 times x minus 3. If I do that to the left side, I'll have to also do that to the right side. X plus 2 times x minus 3. And we can see when we multiply these two, we multiply across, or we can see that the numerator here is going to cancel and you're just going to get x plus 7. And over here, if I distribute this to each of these fractions, notice that the x plus 2's are going to cancel for the first one. And I'm going to have a times x minus 3. And when I multiply this one by this fraction, I'm using the distributive law. In this case, I think you can see that the x minus 3's will cancel. And I'll have b times x plus 2. Another way to think of this is by multiplying the top and bottom here by x minus 3 and this by x minus 3, and multiplying the top and bottom here by x plus 2. And in that case, you can see they all have the same denominator, so you could cancel those denominators if you did that. I'm multiplying this by equivalent of 1 and this by an equivalent of 1. So I'll have x plus 7 is equal to a times x minus 3 plus b times x plus 2. And they would, if I get rid of this and these, then this would be the numerator. The numerator on the left would have to equal the numerator on the right. Okay, so what's the next step here? Well, what we're going to do is distribute this a and now this is where it gets a little bit interesting. What you want to do is kind of like sorting vegetables in the supermarket. You want all the oranges together, maybe, and all the apples together, all the, I don't know, green peppers together, and all the zucchini together. So you're sorting things. And we're going to do that same kind of sorting idea. On the left-hand side, there's only one x. On the right-hand side, there's an ax and a bx. So what's on the left, the x has to equal the x's on the right. Ax plus bx. And from that, I can see the coefficient in front of x is 1. 1 would have to equal the coefficient of a plus the coefficient in front of this term, which is b. And this here is a constant, 7. That would have to equal all the constants on the right. Negative 3a plus 2b. So here I have 7 is equal to negative 3a plus 2b. Now you could solve for, you stop that. Dismiss. Okay, you could solve for a or b and then use substitution here. Or we could use the idea of linear combination, where you want to get the same constant in front of the a, or but a different sign, or the same constant in front of the b's with a different sign. It doesn't matter if you choose A or B to eliminate, just pick one. So I'm going to eliminate A. So in order to eliminate A, I need the same number in front of A in each one of these, but a different sign. So you can see what would I need to multiply that top equation by so that I'd have the same constant in front of A. I think you could see that would be 3. So that would be 3 is equal to 3A plus 3B. I've taken the first line and multiplied that whole thing by 3. And now I'm just going to rewrite for you the second line, just so it's easier for you to follow. And then I'm going to add these two equations. And I have 10 is equal to 5B. From that, we can say, therefore, that B would have to be 2. And if B is 2, can we figure out what A would have to be? Well, I think so. I think you would see that 1 is equal to A plus 2. So A would have to be -1. So we have this and we have this. I'm going to put it on the next page. So my original problem was x plus 7 over x squared minus x minus 6. Oh, I'll pull that down, okay. And we had gotten this to the point where we're going to have the integral of A over x plus 2 plus B over x minus 3. And the goal was to try to figure out what those A and B were. And I think I did that just a moment ago. Let's get that off the other sheet. I think we slide this down. We had that A was -1 and B is 2. So I'll have -1 over this plus 2 over. And now we may not be able to integrate this, but because we broke this down using partial fractions, we can integrate this sum fairly easily. I think we would all agree that the numerator is if I bring the negative out, would be the derivative of the denominator. So we'd have the ln of x plus 2 if I bring that -1 out. The numerator would be the derivative of the denominator, so it would go into the ln of the denominator, plus 2 times the ln of x minus 3, the absolute value, and then plus c. So you can leave it like this, or we could use our laws of logs and simplify it more. But this would be the answer to this integral problem.